Welcome guys in this lecture. So in this video we will discuss about the Z transform in digital signal processing. So guys, before starting the video I want to tell you, please subscribe my channel if you have not subscribed yet, and if you want these type of videos on demanding then of regarding any subject in electronic and communication engineering, so you can contact with me, or you can write that in the comment section. So let's start the video. So basically, what is Z transform? So Z transform basically is a transform that perform the transformation analysis of the signal from time domain to frequency domain, and it performs the transform analysis of a discrete time signal, basically for discrete signals, or we can say some unstable signals in the signal and system. So it analyze and transform the linear time invariant system signals. Basically, what are the linear time invariant signal systems? Basically, linear time invariant systems are the signals basically that have considered the number of the delays in the signals. Basically, some shifted signals or delayed signals that are the linear time invariant signals, and that are not vary with time. So basically, in the linear time invariant system, that is a complex system, it have consider that z raised to power n. We represents this complex system with this z power n, and y of n basically is the output or basically response of this z transform, that is equal to h of z, that is the impulse response of z transform, and z of n, that is a complex system basically. So here if we want to find out this h of z, that will be equal to summation from n, the value of n that may be equal to from negative value of infinity to positive value of infinity, and h of n have some values, and that is multiplied with complex number or complex system z raised to power minus n. Basically, for this z raised to power n have real and imaginary component values. So if we solve this summation value, this behaves like a discrete Fourier transform. Here z is equal to, as we know, the value of z, that is equal to exponential power of j omega, basically that have real and imaginary values. So here if we find out the magnitude of this z transform, that will be equal to unity. So the z transform for the discrete signal, that is expressed as a power series basically. So it behaves like a power series. So here this is the x of z. Here z represents, means we are finding out the z transform of x of n signal or discrete time signal, discrete signal basically. So if we want to find out the z transform of this x of n is basically, this x of n is basically a discrete signal, and if we want to find out this, the z transform of this signal, then we consider as a x of z. X of z means the value of this z transform is stored in the x of z, that is equal to summation of n is equal to minus infinity to infinity time x of n. X of n is basically the discrete signal, and we are finding the values of this discrete signal with z transform, and with that is multiplied with this complex variable or complex system that have a real and imaginary components basically. So here, and after that x of z value, that is equal to basically this is the procedure for finding out this z transform. If we find out the z transform of any signal, that is means this represents this z of x of n, this z represents this. Here we are finding out the z transform of this x of n signal, and that is stored into the x of z. And if we want to find out the inverse z transform, means again the transformation of the signal from this z domain to the discrete domain, then we consider this equation x of n means this z inverse here, this z inverse represents means we are finding out the are converting the z transform, z inverse transform from the z transform. Basically we are considering here the z inverse of x of z. X of z is this, means firstly we have find out this the z transform of this x of n signal that is stored into the x of z. Now we are again we want this z domain to, we want to convert this signal from z domain to the discrete domain this, then here x of n, we want x of n, so here take the z inverse of this x of z. What is the x of z? X of z is basically a discrete domain signal where we have already find out the this z for transform of that particular signal. Here this represent this, so here z transform basically is a infinite series, so it exists only if for those values of the z where the series is converges basically. So and that have also a region of convergence, basically some part that we will discuss in the later videos, and region of convergence in the z transform. Due to this region of convergence we find out our series is converges or not. So this will basically depend on the magnitude of this z transform. So R of C, ROC basically region of convergence that contains set of some values of the z where basically x of z means where we have find out this z transform of discrete signal that maybe have some finite values. If we have, if in the z transform, when we have find out the z transform of any signal, and if that have the output have some finite values, then the region of convergence contains some set of finite values of z, and that will be that contain from the region of convergence from 0 to infinity, that is exclude the 0 and up to infinity. So that will be, we will discuss these things on detail in the next later video. So here in this continuous session, if we want to evaluate this complex number, basically what is complex number, z raised to power n, so are these real and imaginary parts. So if we evaluate the complex number x of this z transform, means here x of z represents means this is the basically expression for finding out the values of z transform. Basically here this is a complex number, z is equal to, the value of z is equal to r e raised to power j omega. R represents the real, e raised to power e, and e j omega represents the imaginary part here. So x of z have at the z is equal to r e raised to power j omega, that is equal to, so the formula of the z transform is, that is summation of where n represents for discrete signal, so the value of the discrete signal that is from minus infinity to plus infinity, summation of all these values with this x of n signal. X of n is the basically this is nothing but a discrete signal, and these for minus infinity to infinity time this discrete signal value that is multiplied with complex component, basically complex system or complex variable here z. So the value of the z that is equal to r e raised to power j omega, and basically here basically in this part that is equal to z raised to power n basically. So here we replace this z with this r e raised to power j omega and minus n, that is same on this power that is considered here. So this thing need to remember here, and here then if we simplify this equation, here this bracket is gone like this. So if we simplify this equation, then that is equal to n is from for discrete values of signal from minus infinity to plus infinity, that is x of n, that is discrete signal, that is multiplied with real part r raised to power minus n. This is basically a real part, and e raised to power minus j omega, that is the imaginary part. So these real and imaginary part are separated from this equation, and if we solve this equation, this summation, basically this summation expression with the n number of these discrete values, then this behaves like a DFT finding out of this system. So if the real value, basically r represents the real value, that is equal to 1, then Z transform evaluated at the unit circle and produce the discrete time Fourier transform of this signal. Basically DTFT means discrete time Fourier transform of this signal. So basically what is this unit circle? Unit circle is nothing but this is the in the Z domain, basically on the origin part we form a circle to finding out the region of convergence or ROC of this Z transform. So basically that is a unit circle that we will discuss in the later videos in the region of convergence part, ROC part. So don't think about this. This will be in the next videos. We will discuss this unit circle, basically this whole topic. So here next we will discuss the some advantages of this Z transform. What are the advantages of the Z transform? Basically Z transform is a discrete time signal for the discrete time signals and linear time invariant LTI systems where the delayed signal is considered, that is completely characterized. So with the help of this Z transform we easily find out the character of this of these discrete time signals and linear time invariant system. Basically we completely characterized these signals basically, and the stability of this linear time invariant system we can be easily determined the system is stable or not, and the stability system of the stability of this LTI system, linear time invariant system, we easily determined, and some mathematical calculation are reduced if we use the Z transform. Basically Z transform is the advanced transform basically. So if we use this Z transform to simplify the some calculations, so it will basically remove some calculations and the lengthy process of calculation that will be reduced. And if we calculate the Z transform, then discrete time Fourier transform and Fourier FT, Fourier transform, fast Fourier transform can be determined. Basically how the DTFT can be determined, that if we evaluate these summation type equations, basically these summation type equations, we one by one the discrete values of the signal, if we evaluate that type of equation, then the DTFT will be determined, and the some entire families of the filters can also be obtained with the help of this Z transform. So that we will discuss in the later videos. So and the solution of the differential equations can be easily simplified with the help of this Z transform basically. So that's all for this video guys. If you really get some idea from this video, then please subscribe my channel, like the videos, and if you have any query regarding the video, then please write in the comment section guys. So thank you guys.